Hello, let's work on our first disordered structure. I'm here in my terminal and I've got the directory open with the ints and HKL files in it. So I'm going to get started with shellxt like we did in the last video. So this is an example where shellxt is going to give us more than one possible space group. Sometimes you just have to go down the list and look at them and see which one looks right, but this one gives us a pretty good hint of which solution is probably the best one. The R factor on the far left is the result of a quick isotropic refinement that shellxt is going to run on each one of its proposed solutions. We can go down this list. There's a few 26, 28, 29%. There's a few around 18%, and there's one at 12%. So that one looks like probably the best option, and we'll take a look at it and see if the structure looks reasonable, if it looks like a molecule. So I'm going to open disorder. Oh, the names are over here. Each one gets a different letter after the name. So this is disorder 1 underscore f.res. How does this look? This is good. This is a totally reasonable molecule. This is a selenourea. It's from the Owen lab. It's kind of a cousin of the first molecule that we worked on. Okay, we're going to go ahead with this solution because obviously it looks fine. This must be the right space group. I'm going to start by naming these atoms and then I'm going to sort them. So this is going to be C1. This is selenium 1. We'll do the right side next and we'll start from 11. This is using mode and name like we did before. I'm going around the ring in order. Escape. And then I'm going to come over to this nitrogen with 2 N-butyl groups attached. And I'm going to start numbering from 21. Okay, escape one more time, sort plus n, file sorted.ints. I'm going to come back to my terminal. I like to have 2 terminal windows side by side because then I can look at my shellxl code in Vim and I can run refinements in the other window at the same time. So let's open sorted.ints in the left window. This all looks pretty familiar, and we can see that the atoms are in order, so that's good. And on the right, we have to, well, we can try running shellxl. We'll see what happens. Shellxl sorted. Cannot open file sorted.hkl. That's because we didn't make a HKL file for this. Now, let's look at the files in this folder. For each one of the possibilities that shellxt gave us, there's a res file which has the structure, and there's also a separate HKL file for each one of those. We'll, I'm going to need my other terminal window back and get out of here for a second. Look at the orientation of these solutions. Some are as input, and that means that the A, B, and C axes are whatever the diffractometer originally decided they were. Some of them have their axes mixed up, and that's because these space groups have a conventional setting. And for example, if you kept the original setting of this solution, 1D, this would be in P2MM. That's not a space group, not for any logical reason, but just because the space group is called PMM2. So the axes get reset sometimes just to follow convention. So if the axes are getting reset, then the indices of all the reflections in the HKL file, they're going to get reset too. So for that reason, we have to make sure we grab the HKL file that matches the res file that we started from. So having said all that, I'm going to copy disorder 1 underscore f dot HKL over to sorted.hkl. Now that I've done that, I'll open my inst file back up and we'll run this refinement. See what this looks like. Alright, the molecular geometry was pretty much stable. We can see the biggest difference features are about 6, 7, 8 electrons, and they're very close to the heaviest atom in the structure. That makes a lot of sense. We can see that there's one positive feature on each side of that atom, and we can interpret that as the atom is vibrating anisotropically back and forth, pretty much perpendicular to this carbon-selenium bond. So everything makes sense here, and as soon as we make that atom anisotropic, we should see a big difference in the R factor and in the difference map too. So that's the first thing we'll do. We'll just go down, put an anis instruction to cover all atoms in the structure, and we'll see what we get here. You can see the R factor dropped from 13 to 6%, so that's got to be a good sign. Let's take a look at the anisotropic model. Okay, well, first of all, around the selenium, this obviously looks a lot better, but around this alkyl chain, now we have some problems. There's a big difference feature that's 2.4 electrons, much bigger than you would expect to see near carbon atoms if everything was normal. Besides that, this carbon, maybe I would call it kind of surfboard shaped, but in any case, definitely pretty unusual for an alkyl chain. Really, for any atom, they don't normally vibrate like that. They don't vibrate so far back and forth. So the most likely thing is we're looking at a disordered chain. So I'm gonna go through the steps that we discussed for modeling disordered chains. We're gonna get started by making those atoms isotropic again. And let's remember what these are. C22 through 25 should be isotropic. I'm going to do that by typing anis 0 before the first isotropic one, and then anis again after the last isotropic one. And at the same time, we talked about getting the quality of the rest of the structure as good as possible, so we can do that. And also at the same time, we'll turn down the occupancy of the disordered chain, like we talked about, to try and get the second part of the disorder to show up in the difference map. So dealing with the hydrogen atoms, I'm going to come over here and label my carbon atoms, so make it a little easier for us to see what we're doing. And now we need to go up to above the first atom. We're going to put in some hfix instructions. Hfix 2,3 for methylene groups, CH2s. This is carbons 13 through 17. Through 17 for the cyclohexyl ring. Carbons 26 through 28 on the 1N-butyl chain. And we already decided we're going to leave hydrogen atoms out of our disordered part until we get a little farther along building that disordered model. We have one methyl group not in the disordered part, which is C29. And finally, we have methine CH C12, and that's hfix 1,3. Okay, let's run this refinement. Oh, yeah, and I forgot about the occupancy of the disordered part. You know, we're going to experiment with this two different ways. I can see that this atom is disordered. I can see that this atom has to be disordered too because I can see the two positions. If these two are, then the last one has to be. But the first one in the chain, is this disordered? It's kind of hard to tell, honestly. So let's start the disorder after C22, and we'll see what happens then. And as long as we're doing that, for now we'll leave C22 anisotropic. Before C23, I'm going to put part 1. We'll set the occupancy. 10.6 is, that's a good starting point. It doesn't have to be perfect. And we're not going to forget, after the last disordered atom, we're going to put part 0. We'll save this file. Now we'll run the refinement. And we'll go right over and look at the result. We can see all the ordered carbons have their hydrogen atoms in place now, so that's a good sign. We can see some stronger difference features around the disordered part of the molecule now. This was already here. This is new, and it looks like it's in a reasonable place that it could be part of the second position of this chain. Finally, this one, just kind of following a potential zigzagging conformation of the second chain. We can guess that maybe this is the second position of the terminal methyl group. There's one more difference feature here. We could wonder if this is the second disordered position of carbon 23, but this other one, first of all, it's a stronger difference feature. It's 1.9 electrons compared to 1.3. Second of all, the conformation here just looks more realistic to me compared to this other one. So we'll go with the stronger difference feature for now, and if it turns out that we need to worry about this later on, maybe we'll worry about it. But for now, we're going to put in a second position of carbons 23, 24, 25, and we're going to use these 3 Q peaks that I picked out. I'm going to come back to my editor. I'm going to change part 0 to part 2, make this 10.4, and we're going to put in a C23B. We'll use these coordinates. C24B is this strong Q peak, the strongest one. And finally, the methyl group. You know what? It's so hard to tell. We're going to use the coordinates of the original C25. In fact, we can just copy C25 from up here and put it down here and change the name to C25B. We'll see how these two atoms sort themselves out like they're supposed to. We have a part 1 and a part 2, so we're going to go back to part 0 after that. And we need to remember we need some restraints to keep these two disordered parts chemically reasonable. Often all you need is to just say that the two parts should look like each other. So we're going to use the same instruction to do that. And we're going to start one atom before the disordered part because we want to make sure that this bond is the same length as the new bond that we're making between C22 and C23B. So the same instruction is going to come before C22, and we're saying that C22, 23, 24, 25 are the same as C22, 23B, 24B, 25B. So let's make sure to get that right. 22, 23, 24, 25 are the first 4 atoms after the same instruction. And we just want to make sure that the other 4 atoms I named are going to be on the same line and in the corresponding order. So that's C22, C23b, C24b, and C25b. There's one more thing that's good to remember for disordered structures. We're going to control the ADPs of overlapping disordered atoms when you have two atoms almost on top of each other. We're going to control that with SIMU for similar displacements. We're going to change the strength of this SIMU restraint. This is the first two numbers after SIMU will give the uncertainty on that restraint, since if you remember it, it gets included as an observation basically when you do the least squares refinement. Then finally I'm going to put in a maximum distance for the SIMU restraint, and that's going to be too short for any pair of non-overlapping atoms. Like for example, this nitrogen and this carbon, they're 1.35 angstrom apart. So if the maximum distance on this SIMU is only 1 angstrom, then this is only going to cover pairs of atoms that are on top of each other. So we have the geometry and the displacement parameters of the disordered part restrained now. So we'll go ahead and run this refinement. The R factor right now without a disorder model is 6.1%, so let's remember that. Now we're down to 4.5%. That's pretty good. Let's see what it looks like. Okay, these two chains, we'll look at them individually with the show P 0, 1. That's the major part. This looks good. Looks like a reasonable alkyl chain. And we'll do the same with part 2. This also looks like a very reasonable alkyl chain. Let's look at both together. We'll see if the geometry of the two parts is consistent. We'll check each of these bond lengths. We have a 1.59 and a 1.56 angstrom bond. 1.59 is a bit long, but maybe not so unusual. After that, we have a 1.49 and a 1.52, which are both fine. And 1.52, 54, those are totally normal. One thing we haven't done yet is refine the occupancy fractions of these two parts. And I can see by looking at them that the occupancy of the major part is probably a little lower than it should be. The minor part probably has a little bit more density than it should. I can tell that because the displacement parameters are smaller up here and bigger down here. So we'll refine that ratio instead of fixing it, and we make that change by coming down to the part instructions and changing this to occupancy of 21 and the other will be minus 21. So remember, now we're setting the first one to the second free variable, and the second one we're setting it to 1 minus the second free variable. So we need to go up to our f of r line. We're going to add a second free variable because the program is going to yell at us if there's nothing there. So that's putting an extra parameter in our model. It's that easy, and that number is going to get refined. So it doesn't matter too much exactly what I type in right now. We'll run this again with the occupancy ratio refined. We can see that the R factor dropped again by just a bit. We could already tell that it wasn't too far off here. And yeah, now the displacement parameters of the two disordered parts of the chain, they each look pretty reasonable. Okay. Well, this is looking good. The next thing we're going to do is add hydrogen atoms to the two disordered parts. That's straightforward for the actual disordered atoms, but it's a little less straightforward for the first ordered atom. And that's because when you put in hydrogen atoms, you need to look at the neighbors of the atom that you're putting hydrogens on. when we use HFix23, it's expecting to find a carbon with two neighbors, like this one, for example. It has two neighbors, so we know where to put two hydrogens on it. This carbon, by contrast, it has two neighbors this way if you're looking at part 1, or it has two neighbors this way if you're looking at part 2, and we don't know which two neighbors should we use to attach to hydrogen atoms. So let's talk about how to deal with that situation, which is not complicated but slightly time consuming, a little annoying. I'm going to go down to C22. That's the last ordered atom like we're talking about. I'm going to put two hydrogen atoms in part 1 to go with this chain on the left, and I'm going to put two more hydrogen atoms in part 2 to go with the second chain on the right. And each one of those pairs of hydrogens is going to be surrounded by an affix instruction. There's affix 23, H22A2. Remember, these coordinates don't matter, but the displacement parameter does matter because we need to tell this hydrogen ADP to ride on the carbon ADP. So the code for that is minus 1.2, and that tells us it's going to be 1.2 times the carbon equivalent isotropic ADP. I'm going to make a second hydrogen, same as the first one, but a different name. And after that, I put an affix 0. Oh, I forgot the whole thing we were doing here. These first two hydrogens, these are in part 1, and they're going to have the same occupancy as the rest of the first disordered chain, which is 21. Okay. Now we'll switch over to part 2. This has the occupancy of the second chain, which is minus 21. And I'm going to put two more of these. Change the names. I forgot my affix instruction before these two hydrogens. This is affix 43 again. After this, affix 0 and part 0. Okay, let's run the refinement with just those hydrogens in there and make sure it looks okay. Missing affix before atom H22D. Oh, I put the wrong affix code. It should be 2,3, not 4,3. It was looking for just a single hydrogen atom there. Okay. What are we doing now? We can look at parts 0 and 1. Those hydrogens look like they're in the right place. And parts 0 and 2. This also looks like it. This carbon looks tetrahedral when you view these 4 atoms attached. So it looks like we did good here. Let's come back here and H-fix the rest of the disordered hydrogen atoms. I'm just going to write new H-fix instructions. 2, 3, this is going to be C23, C24, and C23B, 24B. The two methyl groups, it's H-fix 137, and those are C25 and C25B. Run that refinement again. Now the R factor is down to 3.9%. Okay, still looking good. There's no surprise there. We know the hydrogens are going where we tell them to, so there's nothing that we would be surprised by after just adding hydrogens. We do need to make the disordered atoms anisotropic, and to do that, all we need to do is get rid of this anis 0 instruction that we put to stop them from becoming anisotropic. At the same time, we want to make sure and restrain those anisotropic ADPs. Again, same as with the geometry. It's just that you want to keep it reasonable. You want to tell it to stay looking reasonable and not kind of wander off and do whatever it feels like. Remember that the parameters in a disordered part are less controlled by the data, so we need to make them a little more controlled with the stuff that we tell the program. So the first ADP restraint to use typically is RigU because it's chemically justified. And we're going to put that restraint on the last ordered atom and all the disordered atoms. C22 and C23 through C25b. All right, let's run this refinement with everything anisotropic. How are we looking now? This all looks really good. The strongest difference features, we can see that they're around the selenium atom now, and that makes sense. They will tend to cluster around the heaviest atom. We'll check in with the R factors and the size of the difference map. R1 is 3.7%, and remember we're going to compare that to R int and R sigma up here. These are 4.5, 3.9%. So actually R1 is the smallest number, and that's great. A highest peak of 1.0 electron, that's a little bigger than we would like to see, but it's not such a big deal. And again, the fact that it's near selenium, it's easy for artifacts to show up there, and it doesn't have to mean anything bad. The final thing that we want to check is the geometry of this model that we built, and we want to look in detail. We want to have kind of extra scrutiny on this disordered thing. So I'm going to get rid of the hydrogens for now, just because we don't need them. I'm going to check these bond lengths one more time. We changed the model, we went anisotropic, so everything we checked before, we're going to check it again. We have a 1.58 angstrom bond and a 1.52 angstrom. Those are a bit different from each other, maybe a bit funny. I think maybe I see something else funny here. This is a 130 degree carbon-carbon nitrogen bond. It should be 109 degrees, so 130 really is pretty unusual. And this one is 104. Again, a bit weird. The combination of those two things is making me think maybe, as a matter of fact, we should split carbon-22 in two parts. That's going to be easy to do. We just have to make sure that we fix up our restraints appropriately after we do that. We'll back up the model that we've got right now. Back up sorted.ints. We'll call this before splitting C22. Now if we need to come back, we'll have this and we won't have to do it all again. So I'm going to take C22. First, these hydrogen atoms. If we're splitting the whole atom in half, then we don't need to worry about this whole fancy thing with the hydrogens anymore. So unfortunately, I'm going to delete this whole part. Carbon-22, I'm going to put it inside part 1, and I'll put a second copy inside part 2. Same as before, we can hope that this naturally splits itself in two positions without us having to intervene. We changed the model, so we should change our restraints too. The RigU instruction, now we want it to cover all the disordered atoms and the last ordered atom, which now is nitrogen 21. So I'm just going to write N21 through C25b here. The same instruction, remember, that should also cover the last ordered atom and all the disordered ones. So that means that needs to go above N21. And I'll keep the RigU alongside the same instruction just to stay organized. So now what are we making the same? We have one position of this chain consisting of C22, 23, 24, 25, and nitrogen 21, the last ordered atom that it's attached to. The second position is nitrogen 21, C22b, which we're creating now, and 23, 24, 25b. So the 5 atoms following the same instruction are N21 through C25, and the atoms that we want to match them to are N21, C22b through C25b. All right, and the hfix instructions that we wrote at the top of the file, now we have 2 positions of C22, and we're going to hfix both of them. I'll save this, run the refinement. The R factor didn't change at all, but we're going to see what does the geometry look like in the result here. We can see that those 2 atoms did move apart naturally. They're 0.17 angstrom apart, which is a significant enough difference that we could believe those are 2 genuine disordered positions. Let's check especially on the geometry of this second disordered position here. Are these bond lengths reasonable? 1.54 is right on target for a carbon-carbon bond, and 1.50, that is reasonable for a carbon-nitrogen. How about this angle? Now it's 125 degrees. That's closer to the ideal, closer to 109. Still a bit unusual, but maybe not so much that we need to worry about it too much. Let's check on part 1. We can see by looking at it that there doesn't seem to be any problem here. 1.47 is good for a carbon-nitrogen bond, and 1.54, that's perfect for a carbon-carbon bond. And these are also pretty close to ideal. Do show P to show everything together. There's one more thing to take note of. In this second disordered part, the displacement parameters for this first disordered atom, they look a little strange. It's not so unusual when an atom is 1, closely overlapping with another atom, and 2, when the occupancy is pretty small. It's 34% occupied, so that means we're looking at a total of 2 electrons on this position. And that's not enough to define the displacement parameters very accurately. So it's not such a big surprise that it's a little weird here. Okay, I think we've got very reasonable geometry in the major part of the disorder. We've got not totally crazy geometry in the minor part of the disorder. Sometimes that's the best you're going to do. Even under the best circumstances, a disorder is going to come with a little bit less accurate knowledge of the geometric parameters in that part of the model. And it looks like we got hit by that a bit here, but we did our best to make everything reasonable with a combination of restraints and looking at the structure to see where it needed help. The last part of the job, and as long as we're satisfied with the model here, the last part is to equalize the weighting scheme. And I'm going to do that efficiently with Vim by opening a new pane that has the res file in it. And go down to the suggested weighting scheme at the bottom of the file. I'm going to copy this, come up to the ints file, and paste it in. I'm going to repeat this refinement. When we do that, there's a couple things we can notice. One, the difference map actually got a little bit flatter when I did that. It's common that you'll see the difference between the highest peak and the deepest hole, the pluses and minuses on the map will equalize a bit when you make the weights more appropriate. I don't know why that happens, but it's a nice thing to look out for. And sometimes you can be pretty concerned about the difference map that you're seeing. And once you get a more appropriate weighting scheme, you'll see that it looks better than it did before. It takes a few rounds before the weighting scheme is going to converge. So I'm going to come over here and reload my res file, repaste into my inst file, and repeat the refinement. And then repeat this job a couple more times. Okay, now our weights are pretty much converged. The goodness of fit is 1.05. It should be close to 1, so that's just about perfect. I forgot an atom. What's going on with this nitrogen here? This is only bonded to 2 things, and it should be, I mean, theoretically, it should be a sp3-ish nitrogen, although it's part of a selenocarbonyl, so we know it's going to be planar-ish, but at the same time, it's well, it should have a 3rd atom attached to it, and we know that that should be a hydrogen atom. We can see in the difference map there clearly is a hydrogen there. We haven't talked about hydrogens so much yet, and we're not quite going to go into a ton of detail about putting this in perfectly, so instead we'll get it just about right. It's part of a selenocarbonyl, and that means it's going to be planar, so we'll just use the default planar NH HFix instruction, which is 4.3. Same as for a planar CH. I'll put that in our inst file with the other HFixes. HFix 4.3 N11. And that improves the R factor quite a bit, as a matter of fact. 3.7 down to 3.5. Does look good? Yeah, everything looks fine here. I'll fix the weighting scheme just one more time since we did make some changes to the model. And now we're done. So thank you for watching. Pretty soon we'll talk about how to finish cleaning up this model for publication, but the actual model building is finished. Thanks for watching.